There are three broad categories of machine learning problems. If you've been following along with my other live lessons, then you're probably already very familiar with supervised and unsupervised learning. But allow me to recap quickly before diving into reinforcement learning so we can compare and contrast. With supervised learning, we have some set of information X that we're using to predict some outcome Y. So our goal is to learn some function that uses X to approximate Y. So some examples that we've worked through in other live lessons of mine include classifying MNIST digits. So our X in that case, our input is handwritten digits, and our Y that we're trying to predict is what digit that is. So is it a 0, a 1, a 2, or a 3? In my natural language processing live lessons, we have movie reviews, just the natural language of movie reviews as our input data, our X, and then our Y, what we're trying to predict is whether that's a positive or a negative movie review. Supervised learning can also involve regression problems, so using some information about the market to predict how many sales of a product you'll have or the future value of some stock, some asset. Unsupervised learning does not have any Y labels. That's the chief difference between unsupervised and supervised learning. So in unsupervised learning, we have input data only. And our goal there is to learn some hidden underlying structure of the data X. So examples that we've talked about before in my live lessons include the word vectors, where we take natural languages input and we convert those into word vector representations, or generative adversarial networks. So later in these live lessons, we'll be using generative adversarial networks to learn the structure of some input data, in our case hand-drawn images, to learn about their structure. Reinforcement learning is a different kind of animal. So this doesn't really involve talking about an X and a Y in the same kind of way as we do in supervised and unsupervised learning. In reinforcement learning, we have some kind of agent. So a deep reinforcement learning algorithm, for example. And this agent takes an action in some kind of environment. And after the environment returns two types of information back to the agent. It returns information about the new state of the environment, so how the action affected the state, how the environment appears, and also provides back some kind of reward. So using two kinds of examples that we've been talking about already, with the Atari game example, say we have a deep reinforcement learning algorithm playing Atari, then the actions that it can take are the buttons in the Atari game, the various actions that the character in the Atari game can take, and those impact the environment. So then the Atari game environment returns back information about how the algorithm's action in the environment has changed the state. So for example, pressing right moves the character to the right. So that impacts the pixels on the screen, and so those pixels on the screen are returned as the state to the reinforcement learning algorithm. The other type of information that's returned to the agent is a reward. So in the Atari games, this is simply the point score. So the goal typically when we have a deep reinforcement learning algorithm, some agent playing in the Atari environment, is just to maximize score. With the self-driving car example, the algorithm driving the car is the algorithm, is the agent, and it takes action. So it moves the wheels, it accelerates, it brakes, and so any of those actions have an impact on the car's position in the environment, and if it makes a mistake, hitting another car or that kind of thing. So that returns information about the state from the environment. So the car's sensors are taking in information about the environment, and there's some kind of reward function that you need to create for that self-driving car. So something like points for traveling distance without having any kinds of accidents, for example. So then this, regardless of the particular application, this cycle just continues and continues and continues until some kind of defined endpoint, like in the Atari game, dying, or getting some really high point score that's considered winning the game. In the self-driving car situation, the typical end of this loop would be safely reaching the destination of some journey. So what's the difference between this general reinforcement learning idea and deep reinforcement learning? Well, I already alluded to this a little bit earlier, but I'll reiterate it because I want to reinforce how important this is. Any kind of reinforcement learning algorithm that incorporates deeply layered artificial neural networks somewhere inside its agent algorithm, that is a deep reinforcement learning algorithm. So deep neural networks are really outstanding functions for processing complex sensory input, like visual input or sound input. So deep neural networks are very well suited to taking in the state information from the environment. So in the Atari game, taking in all the pixels on the screen and how those pixels on the screen are changing. In the self-driving car, this is the visual information, maybe the auditory information, the laser, the radar information about all the environmental information happening around the car. And then the second part, so that's the deep part of the deep reinforcement learning algorithm, typically processing that complex sensory input. And then it's the reinforcement learning part of that algorithm that decides what action should be taken given the information that's been processed about the environment. So that's the key thing here with deep reinforcement learning. Typically, the deep neural network is processing the state information, and then the reinforcement learning algorithm decides what action to take, and then that affects the environment, and this loop continues and continues until some endpoint. One of the landmark contemporary papers on deep reinforcement learning is this paper called Playing Atari with Deep Reinforcement Learning, and that's by Min and colleagues. It came out in 2013. This was in NIPS, in Neural Information Processing Systems, and also it was a paper in Archive. At the time, these authors worked at a company called DeepMind, but as a result of this paper, they were acquired by Google in 2014. And so now that company is called Google DeepMind, and you'll be hearing a lot about them over these next few slides. In that Playing Atari with Deep Reinforcement Learning paper, Min and colleagues introduced this DeepQ learning algorithm, which we will build ourselves, a simple version of a DeepQ learning algorithm, later in these live lessons. Their algorithm played 7 different Atari 2600 games. It beat previous machine learning approaches on 6 of those games, and then beat human experts on 3 of them. A couple of years later, in 2015, a lot of the same authors, now Google DeepMind, released another paper in Nature called Human Level Control Through Deep Reinforcement Learning. And in this paper, they used that same kind of algorithm, that DeepQ network that we're going to be building in these live lessons, to really play Atari games well. So what this chart is showing is that everything above that horizontal line shows that our DeepQ network outperforming the human level performance on all of those games. So the kinds of games that DeepQ networks can become much, much better at than humans are ones that require really fast reaction time, that provide a lot of immediate feedback. The games that this DeepQ network were less good at are the kinds of games that require you to explore large spaces and find a key somewhere to open a door. That's the kind of thing that this DeepQ network wasn't very good at. But anyway, amazing to get into a Nature paper with this computer science research. A year later, again, Google DeepMind had another Nature paper, and in this one, it was all about the board game Go. So they have this algorithm called AlphaGo, which could play this very complex board game called Go. Go is a very complex board game that's popular in Asia. It involves 10 to the power of 170 possible board configurations. as a point of reference, that's more than the number of atoms in the universe. And it's a googol, so 10 times 100 times more complex than chess. So in 2016, in this AlphaGo paper, AlphaGo, the deep reinforcement learning algorithm, was pitted against Fan Hui, who at that time was the European Go champion. And AlphaGo defeated Fan Hui 5-0. And those results are reported in this paper. In March 2016, the AlphaGo algorithm went even further, so a even more highly trained version of it. In March 2016, that algorithm played against Lee Sedol. Famously, it was a very popular live broadcast out of South Korea, and Lee Sedol is this eminent Go player. He's won 18 world titles, and so 200 million people worldwide watched Lee Sedol lose 4-1 to AlphaGo. And so what this chart here is showing, the y-axis is an ELO rating, which is a measure of how good a game-playing individual or algorithm is. So the higher your ELO rating, the less likely you are to lose. And you can see that AlphaGo was, had a ELO rating on par with Fan Hui, and then a distributed version of it was, far better than Fan Hui. And so Fan Hui is that green column there. So, the European champion at that time, the professional Dan level. And then there were these, at that time, the other existing algorithms for playing Go, and they are in red columns. And you can see that their ELO scores are much lower than AlphaGo. In 2017, we had yet another Nature paper out of the Google DeepMind group. And this was for something called AlphaGo 0. So the remarkable thing is that this algorithm had no training data created by human Go players whatsoever. It had no guidance, no specific domain knowledge, except for being told what the rules of Go are. So AlphaGo 0 engaged in self-play, iteratively playing against more advanced versions of itself. Eventually, after 20, 30, 40 days of training here, it had a higher ELO rating than the AlphaGo paper from the year before, from the AlphaGo algorithms that beat Lee Sedol, for example. And it defeated that AlphaGo algorithm 100-0, so decisively a better algorithm. The other amazing thing about the AlphaGo 0 ability is that it was trained on far fewer processors. So the AlphaGo algorithm that beat Fan Hui, it was trained on 176 tensor processing units, which are a Google specialized GPU. So 176 for defeating Fan Hui. For Lee Sedol, the algorithm had 48 TPUs, but for AlphaGo 0, it was merely 4. So the algorithmic efficiency is improving exponentially while performance improves as well. It's really amazing stuff. And that's not the end of it, because also in 2017 was yet another Google DeepMind paper with this AlphaZero algorithm. So this was published in Archive in December 2017. In this instance, they trained a single algorithm to play Go, chess, and shogi, which is Japanese chess. Again, like AlphaGo 0, there was no training data or guidance provided to this algorithm. It only knows the rules of the game. But after 24 hours of training, this single algorithm had superhuman levels of play in all 3 games, in chess, in shogi, and in Go. It also defeated world champion programs in all 3 games, just to make the point. So really amazing. Things are moving quickly. To demonstrate to you both that deep reinforcement learning isn't just about making moves in video games or board games, and isn't just about research out of Google DeepMind, here's another paper showing deep reinforcement learning being applied to yet another type of real-world application. So in this paper by Sergey Levine and Chelsea Levine in Peter Abeel's famed UC Berkeley lab, they trained a robot to perform a variety of real-world tasks. So some of these tasks included hanging a hanger, inserting a cube into this cube game, shape game, using a toy hammer to remove a toy nail, putting a cap on a bottle. As a quick high-level overview of how this algorithm works, there were just the images of the robot visual camera systems using images as input into the algorithm. So this is the kind of state information. And that state information was processed by a deep convolutional network with only 92,000 parameters. And that deep convolutional network was output directly onto the robot's motors. So this particular algorithm is an example of a policy search algorithm, which we'll talk about much later on in these live lessons. So this gives you a sense of the incredible things that are possible and that are happening very quickly in the world of deep reinforcement learning. It's worth taking a moment to mention that there are a wide variety of deep reinforcement learning algorithms, hundreds, maybe more, out there in the world. But some of them, of course, are more popular than others and provide great learning experiences to work through. And so 3 of the most popular are a deep Q learning network, or a DQN, the reinforce algorithm, and an actor-critic algorithm. So we will talk about all 3 of those deep reinforcement learning agents in these live lessons. And there are also 3 particularly popular reinforcement learning environments for agents to use as kind of a playground to train. And I'll show those to you now. So the first is OpenAI Gym. So OpenAI is a nonprofit run by, or funded by, a number of famous donors, including Elon Musk. And they have created this tool called OpenAI Gym, which provides lots of different environments for agents that you build to play around in and get feedback, get state and reward information. So this is by far the most popular of the possible environment tools. The second one worth mentioning here is DeepMind's Lab. And so this similarly allows you to have your agent learn in an environment. And this is particularly well suited to 3-dimensional navigation and puzzle-solving tasks in these kinds of 3D environments. The third environment that I'd like to take a moment to mention is Unity. So Unity is a popular environment for lots of video games that humans play, and they very kindly provided an open source infrastructure for people to use for training their reinforcement learning algorithms as well. Finally, I'd like to give you a taste of what we will be doing in these live lessons. So later on, we will be building our own deep Q network. So we're going to use the OpenAI Gym environment to play a game called the cart pole game. We're going to define an agent. So here's that agent box, and so we're going to define an agent to play within an environment, to interact with that OpenAI Gym environment with the cart pole game. And you can see it happening in real time here. This is the game, this kind of pop-out screen. So there's this, I'm going to get into the details of this game later, but basically the reinforcement learning algorithm is learning how to balance this pole on this cart. It's a simple example. It's perfect for teaching because we can have it learn very quickly with algorithms that we can hand code here in these live lessons. Looking forward to it.